Hello, and welcome to the Electrical and Electronic Development for Space. I am Norman Rivera, and I'm going to be here to talk about the customer story on Firefly Aerospace using the electrical accelerator environment. We joined the transformation about a year ago and are realizing all the benefits each day. So before we begin, I wanted to start with an exciting video about what we're doing at Firefly today.
This is the final commit for launch.
Achieving first flight is a huge milestone for a rocket company.
3, 2, 1.
But ultimately, this business is about getting to orbit and doing it repeatedly. We did learn a lot from the first flight. As far as the vehicle goes, we're almost there. In the months since first flight, we fixed the minor problems with the flight vehicle and are ready to get back to the launch pad. What has impressed me most is the growth of the team. When we tested the first flight vehicle, it took us over 18 times on the test stand to get it fully functional. In getting ready for this second flight, both the vehicle and the team performed flawlessly on the first attempt and were able to qualify the vehicle in only one test. Everyone at Firefly is excited about taking the company to the next level. We've gotten smarter, faster, and more disciplined. We are ready for orbit.
Headed all the way.
See you at the launch pad.
All right, so that was an exciting video. So what you saw was our CEO, Tom Merkusik, and we're really excited to get our second Alpha launch vehicle to the launch pad and launch soon. Now that I have you pumped about Firefly, let me introduce you in my background. Again, I'm Norman Rivera. I've been with Firefly Aerospace since 2019, and I'm the lead harness design engineer. Prior to my current role, I've worked on a little bit of everything at Firefly, on the Alpha launch vehicle, on the launch pad at Vandenberg Space Force Base, and now working on the Blue Ghost lunar lander. And before that, I was a mechanical systems engineer doing aircraft interiors and jet engines, and so that's me. For the discussion topics today, we're going to talk about introductions and the accelerator electrical portfolio, talk about the collaboration and integration that we've done using that portfolio, and then how we implemented it at Firefly, the benefits we realized, and then the next steps. Firefly Aerospace is a diversified end-to-end space transportation company. Our motto is, we're making space for everyone. We have 3 different product lines we're working on. So you saw the launch side of it with Alpha. We're currently working on a spacecraft called a Space Utility Vehicle. And then for science and exploration, we have a NASA CLIPS contract that we're going to design and build a lunar lander that's going to land on the moon in 2024. So our facilities are spans across the United States. We have a facility, our headquarters in Cedar Park, Texas, which is right outside of Austin. We also have our production and test facilities in Briggs, Texas, which is another half an hour north of Cedar Park. And then for our launch sites, we have the Vandenberg Space Force Base in California and Cape Canaveral in Florida. This is just an example of some of the tests that we perform at our Briggs, Texas facility. So this is the Alpha Stage 1 acceptance tests. We do a hot fire for 30 seconds, and then we also do a fairing deploy to verify that everything's going to work the first time when it gets to orbit. So we've already demonstrated operations and have collected real flight data on our first Alpha launch. It flew for 2.5 minutes, and one of the engines was lost, and it was an electrical connection that resulted in losing the ability to control the fuel valves going to that engine. So we were able to continue with the flight, and it ended up getting the range terminated the flight and hit the button to explode some ordnance in the rocket to make sure that it falls into little pieces to not injure anyone. So I'm going to show you the slow-mo of the first flight. So despite not getting fully to orbit this time, the mission was quite a quantum leap forward for Firefly and puts us far ahead of the competitors due to having de-risked some of the hardest parts of launch. So we got 2.5 minutes of flight time. That's 2.5 minutes of thousands of streams of telemetry data, and it's far more useful than anything you can get on the ground or in analysis. So we went further than most new space companies got in the first launches. So Alpha went all the way through supersonic speeds, and that was with one engine out, and the primary structure was incredibly robust. So just before the range terminated the flight, Alpha did a couple tumbles in the air just to show off what it can do. We were able to validate a lot of our models and simulations, and we learned how to make them better. And we got to exercise our ground systems. So we have the launch pad with the strong back and the mobile launch platform, and so we got all our procedures down and verified everything works. And the operations team did an amazing job in the mission control. They learned how to work together, how to communicate, how to disposition issues, handle alerts and alarms, and then communicate that resolution. So they were able to practice and get the launch countdown all the way on the first day that we attempted this launch. And this experience is going to be really good for the second launch and future launches on Alpha and even Blue Ghost. All right, so Firefly's approach to becoming a successful business in the new space industry is broken down into these 4 actions. So it's anticipating, innovating, creating, and dominating. For anticipating, it's anticipating the space economy as one of the greatest 21st century growth industries. We also are innovating solutions into the end-to-end space transportation, and then we're creating products using the simple and soonest approach to rapidly develop and deploy reliable rockets and spacecraft at a low cost. We also plan to dominate and defend our market position, and we're really excited to get to the next steps and make it through a successful launch and continue on hitting our milestones on our Blue Ghost project. So before we go into all the accelerator portfolio that Siemens offers for electrical harness design, I wanted to give you guys an introduction on harnesses and rockets. It's the nervous system of the machine anatomy, and it's a very vital part in making sure that everything in the rocket works as intended. As you can see, the first launch did have an electrical failure, and we want to make sure for these next subsequent launches that we address those and are able to rapidly identify any potential hazards and mitigate them by designing them into our processes and drawings. So breakdown of a harness, you've got your main trunk line that's in the middle, and you have connectors surrounding it. We'll have branches that go to each connector, and it'll have a back shell and housings. There's also going to be some harnesses will have ring terminals, flying leads, and loose terminals just used to go through different parts of the vehicle. And some harnesses are going to be really short, and a lot of harnesses are going to be spanning the length of the Alpha launch vehicle. And so each one of these connectors has multiple contacts, and there's several wires that are bundled together, and then we have typically a closeout on each of these ends of the connectors so that we make sure that we protect the wires going into the connectors and make sure that you can't pull on the wires so that it keeps them in place. So here's an example of some of those harnesses on our vehicle. So you'll see there's a bundle that's tied together, and it branches off into different points on the boxes. And then we have connectors, and you can see the density of wires going through there, along with some of the protection around the connector for strain relief, and for we also have protection from fire, from extreme cryogenic temperatures and from any electromagnetic interference and whatnot. So Alpha has 600 harnesses, avionics components, valves, and sensors. That's a lot of parts that we have to keep track of and make sure that they're all working as intended. So each of the Alpha vehicles is slightly different configuration. That's dependent on the payload customer's needs. So we need to be able to take all of these components and make sure that they're configured properly for each individual build of Alpha. As you can see, we have 3 different segments on Alpha. You got the payload at the top. That's where our customer puts their satellite in, and then we got the stage 2 just below that. That takes that payload and puts it into orbit, and then you have the stage 1 booster that lifts it off from the ground and takes it up to outer space. So here's a typical flight profile of an Alpha rocket launch. So we start off with the Alpha vehicle clamped down on the ground onto the mobile launch stand, and we ignite the engines at T-minus 2 seconds. We'll verify that the engines are all running nominally, and then we'll release the clamps and let Alpha fly. So after liftoff, the stage 1 booster runs for about 2.5 minutes before we cut off the engines, and then from there starts a separation of stage 1, which then just jettisons down to the ocean, and then stage 2 engine ignition lights up, and then about a minute after that we'll have the fairing separation. So that's when the payload and stage 2 are in space, where the air is non-existent, to where we don't have to protect the payload. And then you've got stage 2 that runs for about 5 minutes, and then from there we'll go into a coast for about an hour, and then relight the engine for another 3 minutes, and then deploy the primary payload after the second engine cut off, and we'll coast a little bit more, and then deploy the secondary payloads, such as like small sats. So before we jump into the present of how Firefly is using the Siemens software to develop harnesses, you should know about our background and what we were using in the past. We had different applications to define the harness and all of the connectors and all of the pinouts, where each wire went, and so this is an example of our wiring diagram that we built in Excel. So on the left you'll have one side of the harness going to a connection point or a box, and then it'll have details about what it is, a reference designator, what the connector part numbers are, what the pins are, and then the wire types, the wire part numbers, the signal names, and then as you move from left to right you get to the other end of the harness, where it goes to all the different sensors and valves that we have scattered throughout the vehicle. So as far as getting a diagram from box A to box B, we use Visio to define that schematic. We also use Visio for some of our harness drawings to define the lengths for each branch. So on the Visio drawing you'll have the connector with all the different cable types going to it, the reference designators, and then what the length is until it goes into a breakout point, or to the next branch, or the trunk line, and whatnot. To get those lengths on the drawing, we had to either model up in CAD using some of the spline routing tools that they had in there. They're very simple splines. There were no details on the connectors or the support methods to secure it to the vehicle. We were just routing splines from point A to point B and adding a little bit of additional length in case there was any issues when it came time to actually install this on the rocket. We also, in some cases, just took a piece of string and routed it on the vehicle and figured out the lengths and then went and built it. And in some cases, we ended up having too long of a harness, so we had to go through and route in a different way to take up a lot of that slack, or we had to coil it up, which adds that additional slack adds mass that we want to refine and reduce so that we can increase our payload mass capabilities. So a lot of the drawings that were done in on Alpha were documented in AutoCAD Electrical. So that's taking the harness with the links and the different connectors and where they break out, and put it all in one drawing along with the wire diagram that shows you the pinouts going from connector A to connector B and what all those signals are. And then we'll have a bill of materials that's manually inputted to define all the components that you need to build this harness. To install it on the vehicle, we had PowerPoint slides where we would take a screenshot of the CAD and draw some lines by hand, and then we also took pictures of the actual hardware, and either they're already integrated with the wiring just so we can have it documented, or we're also sketching in where the harness goes and where to secure it on the hardware. And then all of that data we store in different locations on the network in some folder structure that's not consistent and all over the place, and it's not very detailed on what the file is or what it's used for and whether or not it's the latest version. We also had a file management application, Autodesk Vault, that also we use to store that data and have some resemblance of a configuration control, like being able to lock a file down and release it and then revise it if needed. So to summarize all this up, we were using 6 different applications to define our harnesses and document them and use those to assemble and produce harnesses that are installed on the vehicle. It was very difficult to keep track, and it was even more so difficult when the person that was putting all this together is no longer around to ask where the right stuff is, where the right information is. So there's a quote by Mark Mulligoli. The harness schedule is always on the critical path of the project. This is because the harness is the last design to be frozen. All the electrical interfaces in the spacecraft accommodation shall be frozen before. Like, we need to have all of our inputs before we can define the harnesses. And so one of the first equipment, harnessing is also one of the first equipment to be installed on the satellite, or in our case, the launch vehicle. So no electrical testing is possible on the spacecraft without this harness. They can't move forward with verifying everything is working properly without the harnesses in there. And so it's a pretty critical step in getting us towards launch. So why Siemens? We evaluated several CAD and PDM softwares and down selected them to 3 options. The first option was to stick with what we know and what we have, and obviously that wasn't really an efficient solution because we were juggling different applications. The second one was a well-known big aerospace software for CAD, and then finally there was Siemens and their accelerator platform. So we evaluated them on different categories, from migrating the data from our old systems to using the CAD interface and using the different applications for like harness routing or fluids routing, and doing composites design, and even just trying to make sure that we have a configuration management control with some PDM system. So we evaluated NX, Team Center, and Capital and found that that met all of our needs for designing harnesses at our company. So that leads us to the present, Accelerator and Firefly. So this is a typical design life cycle where you start off with your requirements, you do some modeling, you drive you come up with different designs, and then simulate those and verify that they're appropriate for the function that they're trying to do, and then we go into production and program delivery. So these are all the different applications that Siemens offers for the life cycle offering, or to go through the life cycle of designing electrical harness. We're only using the three in the middle. One on the left is Capital Logic to generate the schematics and the wiring designs. The middle one is the NX to route them in 3D and get the links. And then the right one is to generate the harness designs and form board drawings. This is a different way of looking at it, but it's a process flow on how we go through from left to right, designing the architecture, defining all the details, and then going through the manufacturing phase. For the design process on the three applications that we use, we have the systems connectivity side using logic on the left, where we'll define all the boxes and define all the connection points from point A to point B. Inputting the pin numbers and where each wire from pin A goes to which connector or box on the other side. And then for the wiring connectivity, we use the Capital Logic. We generate wire diagrams on, and that's where we input all the connectors and other details to further define the harness. And then we go into our 3D design. We are able to synchronize that, bring it into our NX electrical routing software, and route from point A to point B on the vehicle, and then synchronize that with the Harness XC Capital application to define all of the details for assembling the harness. All of these things are linked together. So we're able to synchronize. If we make a change on the logic wiring connectivity side, we're able to easily synchronize that in NX and then bring that back into Capital through the Harness XC application to update the drawings. And I'll walk through all these different steps in the next slide. So one of the things that we benefit from inputting our harness data into the software, especially the NX CAD, is being able to collaborate with the rest of the teams that are working on the vehicle, from fluids, routing all the different plumbing lines, to structures, putting in all the different brackets and whatnot to support all of the components on the vehicle. Teamwork makes the dream work. For starting with NX integration, being able to take the electrical information from Capital and put it into NX, allowing us to go and place connectors in space where they go, and then route the harnesses and actually have it represent the full bundle diameters from one end to the other. Allows us to create space reservations so that if we've got a very congested area where other disciplines are putting their stuff, we're able to identify, hey, this is probably an area that we should coordinate on, or most cases, we'll find out that something is interfering, and that starts the conversation with the other groups on, maybe we should fix something or move something around to get everything to fit in the same place. So we're able to send the wiring data from logic to NX through an interface embedded into NX, and that's through what's called the Embedded Capital Navigator. So this lets us browse through the capital database and find the harness that we're routing in NX, and we're using that to import the connectors and the wiring point A to point B data in NX. From logic to NX, we're able to go through and assign connectors and splices and auto-route the wires all in the NX CAD, which then gets us our bundle diameters and other routing information. So this allows us to go through and check for routing issues such as like tight bends, because maybe some of these bundles could be an inch in diameter, and we want to make sure that we're not pinching them in a way that results in damage. So we're also able to go through, and once we've exported out the harness data from NX to harness XC, we'll put all the details in there. We're able to also resynchronize that with the NX data, so NX has a complete picture of all of the details that we've inputted into harness XC. So for our data management solution, we are integrating with Teamcenter in both NX and Capital. We use a web-based tool, Teamcenter, called Active Workspace. That lets us go through and interact with our data in Teamcenter from any web browser. We can see the designs, all the different bill of materials for assemblies, and then see whether or not that part's been released or if it's still in work or in review. And that lets us go through and know whether or not something is still in design or it's frozen and ready for production. We also have the Active Workspace view from inside the Capital application as well, so you don't even have to leave the Capital environment. And you can also go through the release process from Teamcenter, and it synchronizes with Capital to make sure that the designs in Capital are also locked when files are released. So we're maintaining two different databases with Capital. One side, inside Capital, is one database, and then Teamcenter is a different database. So whenever Capital is ready, whenever we're completed a design in Capital, we're able to publish that information in the Teamcenter, and creates a snapshot of that in Teamcenter where anyone can locate and find it. So the embedded Active Workspace lets us interact with all the different information that we have in Teamcenter, and we are able to find parts, verify, like if we need to go look at a block diagram or schematic, we can reference that from within the Capital environment without having to go through and open separate windows. So between Capital and Teamcenter, there is a lifecycle management for verifying or for locking things down in Teamcenter and then revising them. So the workflows are our ability to go through and send these drawings and data to a review process. We'll have a checker that verifies all the data is correct and meets all the different standards that we've established, and then we'll send that off to the reviewers, who are either the stakeholders or the system owners, to verify that we've clearly documented everything and it's accurate, and it can be built. So we have some of those stakeholders are manufacturing, to make sure that we either have the capability to build it, to procurement, making sure we can actually buy it and get it in the right time, and then the integration folks, that making sure that we actually install this on the vehicle. And through that workflow, we're able to communicate any red lines, as we call it, any changes that need to be made through Team Center, so it's all in one spot. Team Center allows us to have everything in one place, so there's a single source of truth, and if there's ever a question of which data is the correct data, we know we can always refer back to Team Center. So from the designs in Capital, we're publishing them into Team Center along with the bill of materials. So now we have all the data in one place, and all of our downstream customers are able to get that data from, again, Team Center as the single source of truth, instead of having to have the Capital application and figuring out how to navigate through that. So with our design process, if we do have to revise something, or when we have to revise something, we are also able to use Team Center to drive revisions, or even create new configurations of a part, so a new part number, so that you don't have to go through two different interfaces, one in Capital, one in Team Center. You can just do everything from Team Center. So those are all the capabilities that the Accelerator suite offers. How did we implement this? I want to go through the different steps that we took, and I want to emphasize how at each of these steps Siemens was supportive throughout the whole process. We had they brought in the experts to help us configure all of our software so that they all talk to each other and they're all working correctly, and then help us migrate all of our data from our legacy applications into Team Center so that we can use them in NX and access any of the other documents and files that we want to start configuration controlling. So this is not as simple as it sounds, like just copying all the data from one database to Team Center. We actually had to go through a process where we had the CAD data itself, the things that define the CAD data were converted into something that can be imported into NX and then saved in the Team Center. And in parallel, there's also, with that CAD data, there's what we call metadata, or attributes associated with that, to define things like the part number, what type of component it is, if it's commercial off-the-shelf COTS parts, or if it's a custom Firefly internal design. We also wanted to differentiate between documents, drawings, and like the CAD data. So there's different types of metadata that we had to make sure was synchronized with the CAD data and ported it over into Team Center. One of the main reasons why we were able to adopt Capital into our harness design workflow was we had the experts from the Capital team to help us to learn how to use the Capital applications and go through and tailor our processes to define how we document the harnesses in logic and create the wire diagrams, and then also port that over into NX, and then port that back into Capital, into the Harness XC application. So we went through different scenarios of ways that we would use the software, and Capital, the Capital team was able to bring in experts for other areas, such as like using the NX electrical routing tool to synchronize the Capital data and associate them so that they're passed back and forth between Capital and NX seamlessly. And then at the same time, they were also bringing in experts to get us the ability to publish designs from Capital into Team Center. There's also the ACE seminar series, where there's tips and tricks or different ways that best practices that we should be doing to make sure that we're using the applications efficiently and effectively as possible. So we have the ACE seminar series that occur pretty regularly, and they're also all those videos and presentations are saved to where you can access them at a later time. For more structured training, there's the Accelerator Academy on Siemens website, where they have different offerings from instructor-led trainings to on-demand trainings that you can just go and browse and watch a video and hit pause if you want to go through and follow along. And then there's also different activities that you can use to kind of learn the process of doing a specific thing, such as like, I want to learn how to go route a harness. It'll walk through all the different steps to use the interface to get what you're trying to do. So when things don't do what we want it to do, when we get error messages or we're not able to figure out how to do something, we have the Siemens community and the support center at our side to help us find a solution to something that we're blocked on. So it could be something where we're getting an error message in Capital and we can't publish this PDF. Like, I usually start off with searching the Capital communities to see if anybody else has gotten that error. If I don't find what I'm looking for, I can go to the Siemens support website and go through the process of either creating a ticket, and in that process you can search through previous articles or support tickets that were already had resolution or still actively being worked. So the benefits that we realized from using the Accelerator platform was being able to support our goal of rapidly developing and deploying reliable spacecrafts and rockets at a low cost. This is a quote from one of our integration engineers when we went through the switch of using Capital and NX to design harnesses on the second Alpha flight vehicle. So it took less than 3 calendar weeks to go from the first engine bay harness in hand to being completely done integrating all harnessing and performing all checkouts in the stage 1 engine bay. For comparison, that same feat took nearly 10 weeks for flight 1. We did it in about a third of the time and to much higher quality standard. And the secret ingredient was unquestionably having that NX harness CAD. So when we were integrating these harnesses into the onto the vehicle, we actually had somebody with their laptop, and we had this big TV on a rolling cart, and we had that right next to the vehicle, so we were able to go through the CAD, click on each harness, see where it routes, find all the different supports that we route through, or the P-clamps and whatnot, and then know which box we are connecting the harness to. So that saved a lot of time in trying to dig through different pages on the documentation or the PowerPoint slides. We're able to just real time go into CAD and find what we need and do it all in a really rapid pace. So just to provide an overview of the benefits we realize, biggest one was having a single source of truth. In earlier slides, I showed you all the different applications that we use to collect the harness data and build it and install it. Now, and that was stored in all these different folders and a PDM system. Now we have a single source where we can go into Team Center. Anybody can access it through a web browser, and that's where we can have configuration control and, in addition, keep track of which harness goes on which vehicle. So we have the ability to do effectivity and know where or which different vehicle it's going to go on. For design, we're able to design in parallel and with intention. So that's being able to collaborate and coordinate with other disciplines to make sure that all of our harnesses are taking up the same space. Sorry. We're able to design in parallel with intention, collaborating and coordinating with all the other groups so that our harnesses are routing around all the different structure and fluids lines, and so we're not interfering with each other, and we're designing that up front rather than waiting till later, which then we're last to design, and now we just have to deal with if we need a cutout, well, we can't get a cutout because structures is already done. So now we're able to do that up front and in parallel and define all the requirements, because it's a lot easier to revise something if it hasn't been released, or even worse, if it hasn't been built yet. So with on the previous slide, there was a quote. It took 3 weeks to do something, or to install all the harnesses in the engine bay, and where it normally took 10 weeks, and so that's a 70% reduction in the harness installation and checkouts. For the amount of time it took to convert all of that data from the legacy software to Capital and the Next was about 4 weeks. So even if you add up the amount of time for design engineering to convert that information with the time it took to integrate, so that's 4 plus 3, that's 7 weeks of engineering and production to get everything installed, versus just doing installations and checkouts on the first Alpha rocket. It took us 10 weeks. So even then, if you take into account the amount of time it took to put everything in the Capital and the Next, we're still seeing the savings. We also have some capabilities with taking the PLM or the XML files from Capital and going through writing different scripts that can extract some key data from those XML files and use that to develop some automation capabilities with being able to quickly synchronize between different tools or devices for harness testing, verifying that the harness was built correctly, and also verifying that our harness design meets the system architecture, which is defined in different applications. We're also able to increase our accuracy and reduce the amount of rework going through all these different tools now that we're designing in parallel with intention, we have a single source of truth, and we have all these automation capabilities that allow us to do design rule checks, making sure we're using the right size wire in the right contact, and so on and so forth. Our bombs, we now have accurate bill of materials for kitting, so we're able to define all the different details of what it takes to build a harness, and so you're no longer relying on just tribal knowledge that you need to have, this part to complete this harness assembly. We're now putting all of that detail in the engineering drawing, so that that is your source of truth, and that's what's driving the flight configuration or the final configuration of this harness. So we're documenting everything. For production, we are able to go through and provide all those details and show where they go, and then we can even do full-scale form boards so that the production shop can route all the cables and wires from point A to point B, C, D, and not have to guess or keep track of where each of those wires go on the connector. So it improved our production's ability to build the harnesses accurately, instead of going through and reworking things because there were mistakes made in interpreting the old drawings. We talked about automation, one of which is being able to verify all the harnesses are pinned correctly. So we have a harness tester machine that goes through and checks for continuity between the appropriate pins and makes sure that each of those wires are isolated, we don't have any shorts, and then we don't have any issues with intermittent connections. From there, once we verify that the harness is good, we're going and putting the harnesses into a hardware in the loop test where we have all the boxes before they're installed on the vehicle. They're all on the table, and we're able to go through and verify that they all function correctly before we put them into the vehicle where it might be in a hard to reach area. So we want to make sure that everything works before it gets installed on the rocket. So for the engine harnessing, we had multiple iterations of the harnesses on the engines, and having these in Capital and NX allowed us to quickly copy those designs or revise them as needed to keep up with the changes that our propulsion team was asking for. So we're able to create different configurations of the harness so that they can do different tests and find the appropriate ones that they want to use for flight. And so, this allowed us to keep up with their pace, or actually get ahead of them, so that we're not spending lots of time trying to rework and come up with all these different configurations. We're able to just rapidly document those different configurations and release them so that we can focus on other things, such as routing all the harnesses on Alpha. So like I said, there's over 600 components on Alpha, including harnesses, avionics boxes, sensors, and valves. So there's a lot to keep track of, and there's still a lot yet to be done to get all of that documented in Capital and NX. All right, so the future. We've only focused on the center of the Capital and NX accelerator platform. We've only been looking at wiring schematics, wiring diagrams, and NX, and look at all the different benefits that we've gotten from it. But there's more to come with ways that we can leverage all the different offerings in the accelerator platform to help us continue to improve and realize the benefits from the software. So one is with systems engineering up front, defining the architecture. Next one would be the PCB designs. All of our we have an in-house team that designs and develops the core boxes that are used to control and collect data and communicate with the ground systems. Then there's also the manufacturing side, where once we take our harness drawings, we want to be able to go through and make the manufacturing more efficient by automating some of the things of creating assembly work instructions, or having a link to our ERP system for the bill of materials and procurement. And then being able to publish that data into an easy to access form. So it's not just a PDF. There could be kind of an interactive 3D manual that shows you how things are put together. So that could be useful and for the future when we go into reusability on a future vehicle. So with that, I want to thank y'all for attending, and I want to thank the Siemens team for inviting me to speak at this conference. And I'm excited for the future of Firefly and Siemens to help make space accessible for everyone. Thank you.